So today we're going to talk about threaded fasteners. So what are we talking about? Bolts, screws, that kind of thing, right? So we've got little bolts, and we have
big, humongous bolts.
big ass bolts. We got things that are different. Kind of like a screw, but not really. Okay. So, let's go over some terminology here. So anyone know any of those terms? Any of those measurements?
Thread.
What thread?
Crest. Screw.
Where's the crest?
External.
Yeah, the top of the thread, that's the crest. So the root's the bottom. What about this dimension? All the way across. From crest to crest. What's that? From the crest to the crest. What's that measurement? Major diameter. So that's our major diameter. So what do you think from the inside to the inside is? From root to root? Minor. And what do you think the halfway point to the halfway point is? Pitch. So what is pitch? Or let's wait a minute, we'll talk about that in a second. What's this? The pitch. I just said we'll talk about it in a minute, we'll talk about it. So that's the pitch. So the pitch is the distance from one tooth to the next tooth. It's also, on the pitch diameter, that's where the two teeth are actually doing most of their touching. And it comes from gears, because gears, the pitch is exactly where they touch, because the gears only touch in one spot. With threads, they kind of touch along that whole face, but theoretically the middle of it, so that's the pitch. Which one of these three dimensions do we use when we talk about screws? Right?
Major.
Yeah, we use the major diameter. We're talking about a screw, we'll talk about its major diameter. What about this? What's that?
Axis.
Yeah, that's the axis. What's this one? The measurement from the crest to the root. The depth, right? And what's this thing? The body. And let's see, what about that? Without looking at the answer sheet. What's that? Yeah, the included angle. So that means it's the angle that includes that gap. And what's this? Threads per inch. So if I line up 0 with one tooth, that tooth doesn't count. So I go 1, 2, 3, 4 on the next inch. So that's 4 threads per inch. It's not 5 threads per inch. Another way to count it is if you line up the tooth, count the spaces. 1, 2, 3, 4 spaces within that inch. Okay? And what's this on the end? The chamfer. What's the chamfer do? Yeah, it makes it so you can start the bolt, right? Have you ever cut off a bolt to make it shorter and then try to start it?
Yeah,
That's fun, huh?
always.
Put your nut on first, then cut it.
Yeah.
Yeah. So, any questions on the terminology for parts of a screw? Yes, no, no? All right, so we have a few different thread forms. So this is the way that threads are shaped. If you go to the hardware store and you buy a screw or a bolt, what thread is that going to be on it?
Standard.
There is nothing called standard.
American National.
So the American National, Unified National, Metric. Which one is that? No. My thing doesn't show up. It's unified. Unified. That's what it is. Because on the bottom, they cut it with a tool that has a radius usually. And unified, round, it's pretty close. So radius on the bottom, a little flat spot on the top. Why not a flat at the bottom? Yeah, because doing flat inside corner, sharp inside corners is really hard. And also, you know, you have a sharp corner, that's a weak spot. So this, you got 2 weak spots for every thread. Here, no weak spots. So you go with unified, 6 degrees between them, and then the pitch. And we kind of cut off the tip. Why do we cut off the tip of it? No, because that's external corner. Why do we need extra space? What do we do down here? Down here is not sharp anymore. So up here can't be sharp. So this is cut off, so it'll go down in that area there. So down here, because it's not sharp here for that line, it's made so that that flat spot can fit right there, above that curve. Otherwise, they wouldn't go together. What are some of these other ones? What's this? Oh my God. What are those?
Acme.
Is that Acme or is that square? Just further underneath there. It's square, right? If you look at these ones where it's looking straight down on it, the teeth are the side of the tooth is going up and down. The angle here is just for the teeth going back to the next thread. So that's a square. Why would we use Acme or square threads? What?
Something real tight.
Lots of pressure.
Yeah.
Yeah, you need a lot of strength because now you've got some bulk there that can handle something.
Yeah. Like on bunnies.
What about that buttress thread? The buttress over there. Why would you do that?
Stronger one way than the other.
Yeah.
Maybe you have like a quick acting vise.
Yeah.
You could have it where it push on it that way and push up the gate, and then go back the other way to lock it in. What about knuckle?
Some running kind of loose.
What?
Some running kind of loose.
Not necessarily. It could run. It could have a tight fit with a knuckle. But now we've got the same width as we had with the square, but we don't have any of the sharp corners. Now it's not going to have those weak spots. So when we're looking at screws, we have class of fit. So this is fine. No. You have different classes of fit. So the class of fit is how tightly the threads are going to fit together. So class 1 is a loose fit. So we use that for quick assembly things. So class 1, you can put the nut on it and spin it in your finger and it'll go around a couple times.
Like a wing nut?
Yeah, like some wing nuts. But you can hit it and it's going to turn a couple times without you turning it. Makes it easy to put on, but it's not quite as tight and it doesn't line things up as much. Class 2 is a high quality, and that's the one we use most often. So class 2, you might be able to spin it a little bit, but it's not going to keep going. And usually, you might have to use your fingers to tighten the whole thing. Class 3 is the very high quality, where things are high stress, high vibration. And so, can you use your fingers on that? No, you have to use a wrench the whole way.
Like torque bolt?
Yeah, anything if it's going to be vibrating, you don't want it to vibrate out. So you'll do a class 3. So things like Loctite, what that does is it turns a class 2 into a class 3. So like if you use the temporary Loctite, it'll turn the 2 into a 3. Because it takes up that extra space. And that has to do with kind of what the tooth form is and how the spacing on it was and everything. So thread lead, all three of those look the same, right? You notice anything different about those 3 drawings? Besides the dotted line.
The angles of threading.
Yeah, the angle of the thread is changing between that drawing, and that drawing. So that's the angle there. And now you can see how much different that angle is. It's off by half a thread now. Over here, and now that's off by a full thread. So what multiple leads do is that normally when you turn the screw 1 revolution, how far does it go in? If you turn a screw 360 degrees, how far does it move? 1 thread length, right? So by doing multiple lead, what we're doing is we're increasing the angle of the thread. So that way when you turn it 1 time, it goes in 2 thread lengths. Or when you turn it 1 time, it goes in 3 thread lengths. So that's what multiple lead thread does. A way to tell if it's multiple lead is that when you like the end of it, how many times does it start? So if you come over here, go on, get up. Going on a field trip. So right here, this screw, this is the lead screw for it. It has how many ends? How many starting points? 4. Yeah, it has 4 starting points. So that's a quad lead screw. So every time this turns, instead of going that far, it's going 4 threads length worth. And so why do they do that?
Make it
So that
quicker.
it can move faster.
Yeah, so you move faster. Why not just make the threads further apart?
So
Yeah.
that makes
What
it-
happened? It'd make them deeper, right?
Yeah.
Could you make a thread for this wide and that
make
deep?
it weaker.
It wouldn't fit on this piece here, right? So that's why we do multiple lead. So we can get keep the thread depth down, but increase how fast things will move along it. So questions on multiple lead now? Does that make sense now?
It's like,
That's been something that's been always hard to explain. And when I got that, that was one of the first things I noticed. Like, hey, that's a multiple lead thread. I can teach this now.
but like the pitch is different, right? Like-
No, the pitch is still the same. Because the pitch is still the distance from one tooth to the next tooth. It's just now, instead of going from one tooth straight to the next tooth, now we're skipping teeth. And so the pitch measurement itself is still the same. It's just now we have a multiple lead on it. So on the notation, we'll call that out. And that's what we're going to talk about now. So when we call out a thread, we're going to call out the major diameter. This is a standard or an Imperial drawing, so we're going to call out the threads per inch. Then the forms, Unified National. And then the series. So within Unified National, we have different series. We have coarse, fine, and extra fine. And so that corresponds back to the threads per inch. So quarter 28, or quarter 20 is UNC, quarter 28 is UNF. Not all sizes have fine dimensions. And I had a, there. So later on I'll get to the thread chart so you can see what those measurements are. So major diameter, threads per inch, form, series, the class of fit, so the 1, 2, or 3. What was a class 1? Loose fit, right? So here we're calling it class 3. So that's a what? A precise, a very high precision fit. B means that that's a hole. So sometimes we'll just do a note like that. Half 13 UNC. Sometimes you'll see it just half 13. Sometimes you'll see the whole thing, 13, 3B. Or in this case, a 2A. 2A and A is an external. So B internal, A is external. And then if there's anything else after it, like left-handed or multiple lead, you'll make that a dash and then whatever that is. So why do we do left-handed threads?
Goes against rotation.
Yeah, so things that are spinning, we don't want it to loosen while it's spinning, so we can make it left-handed. What else can we use a left-handed for?
Pole locks. Yeah.
Yeah. So, was it oxygen, right?
Yeah.
No, it's
Or acetylene? Yeah. Acetylene is left-handed instead of right-handed. So, and why do they do that?
So you don't put the wrong.
Yeah, so you don't put the wrong one on the wrong. And so they'll also do that sometimes for the lead, instead, or they'll change the pitch on them. So one fitting will be a coarse thread, and one fitting will be a fine thread, depending on what you're doing. But with acetylene, they do it left-handed, so there's no possible way that you can even cross-thread it to get onto the oxygen.
Yeah, all the
Yeah. So we can also expand that node out some more. So we can also tell it the tap drill size. So the tap drill is what makes the inside hole. So we can specify on a drawing a tap drill size. If there's no tap drill size specified, it just tells the thread. you go to a tap drill chart, and it's up to the machinist, whoever's making it, to figure out what size to drill the tap drill. If the designer specifies a specific size on it, that's the size it needs to be tapped, or that the tap drill needs to be. Then next, sometimes it'll be on the same line as the tap drill size, sometimes the next line with the depth of the tap drill. So depth of the tap drill. And when we measure holes, we always measure to the flat, to where the wall of the hole goes. So here the 1 inch goes all the way down to there. Then the tip is on the end.
Doesn't that, the little line with the arrow, that's from the
That's
surface,
depth.
the surface down, right?
Yep. So from the surface here down. And then the tip is on the end. Why do we do a little thing like that at the end? Why does it have this little arrow at the end? This is a drill, right?
Yeah.
End of your drill has a tip.
So is the tap.
What angle is that there? What angle is that? While I get it hacked. Do you want to figure it out?
Show you the angle of the drill. Okay.
What's the angle? What's this included angle between those two lines? Come on, it's easy. What?
45?
Really? That's a 45-degree angle from that line to that line? It's 120, actually 118. We just draw 120. So that'd be 30 degrees there, 30 degrees there. Would you do this 120 in between?
Yes, 59.
And then we call out the thread and the depth of the thread. Why do we leave extra space? Why not make the threads go all the way to the end of the hole?
Well, the started threads on the end of the hole.
So this 175, that's the last good thread that you can use. Why do we leave extra space at the end?
We have the threads to go.
Well, the tap doesn't go,
Started
the
there.
tap doesn't go all the way down to the, thread always goes. Yes, the threads don't go all the way down. It turns on the tap.
So there's a tap. And so till about here, we don't have full threads. So these threads here aren't full depth. It means it's not usable threads. So that's what that end space is to take care of those last 4 threads or so on the tap. 4 or 5 threads on the tap that aren't usable. Otherwise, can we make good threads all the way to the bottom? Could we possibly make good threads going all the way to the bottom?
Yes, not tap, no, the regular tap.
Not with this tap, right?
No.
So this is a gun tap. So gun tap, no. But I can come back with a body aiming tap, which has full threads the whole distance, and get that in. Why would I want to do it this way and not just make them go all the way to the bottom?
Because those taps are very disturbed.
And they're a little hard to work with. Oh, why? But it can be done. Why would I want to do it? What do we care about? Okay, what's your boss care about?
So we're not quick.
Money,
Money and time.
right?
Time and,
If we bottom tap it, that's the second operation. It's going to take more time, and that last little bit's going to be slower. You're going to break tools, maybe if you don't go slow enough. Just more time, costs more money to do it.
don't you have to go down and back down?
Yeah. So usually you just do that. If we have the space, we'll just leave the extra space in the hole. You run it down, one shot, it's done. the metric thread nose kind of changes things up a little bit. We still have the major diameter, but now we tell it an M in front. So we know right off the bat this is a metric thread. Major diameter in what measurement? Oh, so millimeters. And then the pitch. So this is telling us that it's 24 millimeter diameter. That the pitch, the distance between the threads, is 2 millimeters. Okay, so no longer is it threads per inch, it's just the pitch. And they don't have to have it the UNC or anything because we're telling them it's metric up front. Okay?
Is that the top, the piece between the top and the?
But between two crests or between two roots. Okay, questions? So we also have different thread grades. So what is the thread grade? What?
Or like the
quality
size
of
of
the
the-
material.
Oh,
Yeah, strength and
strength.
Yes.
So the grade is the strength of the bolt. So which one is most common?
Yeah, I agree with that.
Okay, this is a grade 5.
Yep.
You can look at the top of the, and look at the lines on it to see what it is. So I can see right here, 3 lines, grade 5.
Yes.
What kind of stuff do they use grade 8 for?
Machinery.
Yes, machinery, but what else?
Head bolt.
Yeah, head bolts, car stuff.
Yeah.
Yeah.
So engine parts, suspension parts.
We used to use it on
Something's gonna be in our head truck.
Yeah. So anything that needs to be real strong, grade 8. So here's that thread table, and I've got the link. Or if you just go on the Google and type in tap drill chart, you'll get, I don't know, a couple thousand websites with these on them. Which one you go to doesn't really matter. This one I like because it has the size, the major diameter, your threads per inch, and it'll show you the coarse, the fine, the extra fine. It'll actually tell you what the minor diameter is. But then we also have the tap drill, and depending on what material we're going to, our tap drill isn't the same as our minor diameter. We'll actually use a bigger tap drill than would normally that would make the minor diameter of the hole. So like here, this is a 75% thread, that's a 50% thread. So this here, the minor diameter would be 0.044, and it'd be now it's 0.05. It's like halfway between the minor and the major. Why do we do that?
Use something to cut out things to it. It's right.
Yeah, it's easier to cut. Because now that the thread, our tap is bigger, or our hole that we're starting with is bigger, we only have to cut out half the material with our tap, right? Why is it okay to use only 50% of the thread with steel? So let's. So here's
Stronger.
my male thread. And then there's that hole that's cut out at 50%. And let's say that here, this is it at 75% for aluminum. Why is it okay to use less on the steel than the aluminum?
Steel is stronger? Yeah.
Yeah.
But where's that line? Or where should it be? Oh, look at this one. Look at those ones. It's halfway up, right? Where's the thickest part of the tooth? Well, at the bottom, but when you look at here, that'd be thick here than there. But the middle is the thickest of both of them. So if you use a 50% thread depth, you're still at the fattest part of both the male and the female thread. So in most uses, that's fine. If you're doing like aviation stuff, you want full threads all the time. But it kind of depends on what your purpose is. And this also has clearance drill sizes. So if you want to have a whole, like, there's a part, and there's a part, so it's going to go down and thread into that. On this part, you'd want to have a hole that's a little bit bigger, so you can go through this hole and then into the thread below it. So this is your clearance drill, showing you the sizes available for that. And those are kind of recommended standard sizes. Okay. Questions?
How come someone say, well, I know the drill, when you had the drill chart, they have all the specific numbers, but
These?
then like some of them say like 116.
Yeah, okay, let me actually open that up for you. So that's a good question. So if I go down this chart, as we're going down the drill sizes, I've got numbers starting at I have 3/64, then I have 53. Then I have 53, then 50, then 47. So these are numbered drills. So drill sizes, you can have fractions, you can have letters. So kind of when you get down to this range, under half an inch, you start getting to letter drills. And then when you get down to about a quarter inch, you make the transition to number drills. And so it starts from Z being big down to A being small, and then it goes from 1 being a bigger drill down to the higher the number, the smaller the drill bit is.
Isn't it like half an inch?
Yeah, it's right around there. And you can see down here, like in this on like the 5/8. Now we have the coarse, the fine, the extra fine. Okay. So, any questions on those? And they have a little printable one that you can save off. Questions? All right. When we draw threads, there's 3 ways to draw it. We can draw a detail, where we show the entire thread. Which of those 3 do you think is the detailed one? The first one, right? You can actually see the threads on it, right? You actually see the threads on it. So that's the detailed one. And so we don't use it. Why? It takes time. Why don't we do it? Because it takes time. Time is money. It doesn't do anything for the drawing to make it look like that. So why do it? It's just wasting time. What about schematic?
Isn't like the threads, the bolts and stuff all gonna be just in a part system?
Yeah. If it's standard, you're only going to draw it on assemblies. But if you're doing your own custom one or you have a threaded piece on it, then you just don't need to draw them. So which of these 2 do you think is schematic?
On the right.
This one? So yeah. So that's schematic. It's a lot easier than that. We have thin lines for the root, or for the crests, thick lines for the root. So it's a lot faster than that, but it's still a bunch of lines. But simplified, easiest way to draw it, that's how we do it. You draw the major diameter, draw hidden lines at the minor diameter. That's it. So if we're looking at it from the end view of a male thread, it's just 2 circles. Right, because you have the circle for the minor diameter, the circle for the major diameter. we're looking at a hole, why do we show the minor diameter is solid and the major diameter is hidden?
Minor is what you see.
Because the major didn't.
Yep. So if you're looking through, it, you're seeing right through the minor diameter. The major diameter is kind of up in there hidden. You can't see it, so that's why. So if you ever see this, and you see that, you know that, okay, that's a screw. So two parallel hidden lines that are grouped like that, probably going to be a screw of some kind. When we section it, the minor diameter is our solid line, top line, so the major diameter becomes our hidden line. Why do we do that? Why don't we stop the hatch at the major diameter?
Because you're going through
That's not where it fits level.
Yeah, because it just got it, because at the top, there's still stuff that's coming down below it. But the minor diameter, there's nothing that goes below that point.
Yeah.
But why do we show that as a hidden line, not a solid line? For the major diameter.
Because you're not gonna see it.
You wouldn't see all of it?
Yeah, because it's not, this part right here isn't all the way solid or all the way empty, right? So remember how we did ribs? We didn't section those because it wasn't really there all the way through. Here, there's a piece there, then a piece there, then a piece there. So we draw the hidden line because there's not really an edge there. That's how deep the threads go. Here's an example of, so through hole, a blind hole. So blind just means the hole doesn't go all the way through. And a bottom tapped. Okay. Questions? And also when we're drawing them, we don't have to draw that space exactly the same as what it really is. So if that space from the major diameter to the minor diameter, if when you draw it, your line's going to be too close together, you're not going to see the difference between the two lines, just make the space bigger. Doesn't have to be exact. They're not going to cut it based on what you draw. They're going to cut it based off your note. Okay? So you make it big enough so it looks good. You can see you change the chamfer also up here. Because again, they're not going to make this chamfer a specific size based on your drawing. It's going to be whatever you call out. Okay? So, bolts go through things. They go through two parts. And so, here's a bolt. That's a bolt. Here's a bolt.
I remember focusing that.
Yeah, that's a bolt too. Is that a bolt? Really? No, that's not a bolt. But also, the main thing on a bolt is it's got this big space where there's no threads. Whereas a cap screw is usually threaded all the way up.
Yeah, but doesn't it have a different kind of bottom?
It could, but not necessarily. Throw a fly pin. So bolt goes through two parts and has a nut to squeeze it together to hold it in place. A cap screw can be longer than a bolt. It also threads all the way up, and it screws through one piece into a second piece. So that it's actually going into another part. And then what's a stud?
Not really.
So a stud is like this. Threads on two sides, so you can thread it into one place. have other threads for something else to a nut to go onto. Do the threads on both sides have to be the same?
No.
No. Do they have to be the same type of thread? No. If you go to Ford, you can get studs that are metric on one side, Imperial on the other side. Then it's not stud. Stud is screw threads on both sides. So cap screws can also have a socket head like that. The reason I wasn't calling this a cap screw before is because the threads are only down here. This is probably gonna have a nut on this side, but it's a socket head. What goes in there? Allen wrench. So socket head has an Allen wrench that goes inside. That's a big one. Probably use that as the Allen wrench for it. So the next one. Now what is this? It's a machine screw. Bolts are big. Machine screws are small. I don't know where the cutoff is, but I don't know, somewhere around an inch. You can get machine screws up to about half an inch or an inch. Anything above that's a bolt, but you can have bolts that are smaller than an inch, right?
Yeah.
What kind of heads do bolts usually have? Hex or squares? So, bolts, hex, square, or socket. So those are usually the ones for bolts. Machine screws, we have a bunch more options we'll talk about in a minute. We also have set screws. Not set screw. Like that. What are set screws used for?
Holding something in place.
You hold something in place, right? So here, I've actually got a couple of set screws. I mean, to lock this pipe onto another pipe that fits inside of it. So they just push on to hold something in place. We'll come back and watch that later. So, machine screw head. So, what kind? Yes, you can watch it again.
He gets to watch it again too, the same way.
What kind of head is that? You know what kind of screw head that is?
Choose.
No.
Well,
You guys are all fired.
well, red shirt?
What?
Well,
No?
yeah. What kind of head is it?
Yeah.
Like, is that Mexico's head or something like that?
No, that Phillips doesn't have a head.
Oh, okay. Okay. No comment now.
So,
Alright.
it's a pan head. Pan head. This is a round head. That's a round head. What about that? So it's got an angle here and it's got a little dome there. That's an oval head. And then what's that?
Finger.
What's that? Oh, it's not said screw. Really? I just said it.
Closer.
What is it?
Allen. We can't see inside. I was thinking it's the thumb.
It's a socket head.
Or Alan.
They deserve it, huh? So that has to be a socket head. So we also have other ones like cheese and binding and all kinds of stuff. We can do 8 hexes still. What's a benefit of doing like an oval or a flathead?
You want to reflect the material?
Yeah, just flush the material, but also what else does it do? Yeah, it has a countersink in it. So what does that countersink do? It centers the holes. If you had a pan head or a hex head, your holes don't have to be centered, right? If you use a flat head or an oval head, it's going to make your holes centered. So if you wanted to be able to use that to make things centered, then you can use the oval or the flat with a countersink on it. If you want to be able to have some adjustability, then you don't want to use something with a flat bottom. How could you make a flat bottom like a pan head or a hex head flush with your material? So,
Use a plug for it?
so if I've got my material top there, and I want my hole to come down, here's my actual hole that I want. But I want it so that my head of my fastener can sit there. What kind of hole is that? Yeah, it's, no, not a countersink. So like there's my material, there's the outside hole, there's the inside hole. What kind of hole is that? What?
I guess you're right, but I'm just gonna see if anything else.
Anybody? AJ?
Board.
Counter board. So counter bore has straight sides. If you go down, counter sink has the angle. Then we have the drive types. So how are you going to drive it? So now is it going to be slotted or Phillips or posi or pin and Torx? Like this little tiny guy is pin and Torx. Little tiny flathead pin and Torx thing. Why would you do a pin and Torx?
Well, it's tamper resistant.
Yep, it's tamper resistant unless someone has a small screwdriver.
Yeah.
Because if you get a small screwdriver like that, you can take it out. Small, straight. So I do at home. I have a little set of jeweler's screwdrivers. But I've also got a set of pin and Torx things I got from the hardware store.
So you just get bored and you take a flat head screwdriver and try to.
Yeah, I just didn't feel like going out and actually getting the right tools. But that goes on here. What do you think what this was for? This goes onto here, which this went on the ceiling, and this held the projector. And so it was pin and Torx, so you couldn't get this off of that. So there's Torx, there's squares. What do you guys like to use?
Phillips.
Phillips?
Anything I can get my hands on.
Is this what? Did you know you were going to do this today? That's why you asked me earlier about screws?
No, actually I didn't.
Because I forgot them. I have some deck screws that I use. That I go and I get these. They're really good deck screws from Osh, and they're Torx. Why do you think I pay the extra money for a Torx rather than a Phillips?
Because it Phillips just twist out, spin them out,
Strip.
torch them out.
Yeah, Phillips, it can strip out, and with the shape of the Phillips, it can go out here straight on. Although here, it's not going to fall off the screwdriver. I can put on the screwdriver and move it around as long as I don't point it down at all. The screw is going to stay on the end of the bit.
Yeah.
I can kind of get in there and adjust it and change whatever angle I need to, and it'll stay on there and go through. It's not going to get lost. No, without a magnetic tip. So just the shape of the Torx, it's not going to fall out. And also, it doesn't slip at all. It never slips. So I can actually drive screws through 2x4s. Like all the way through.
You've done it?
What?
You've done it?
Yes. Several times. I drove it almost all the way through a 4x4.
Really?
Yeah.
As long as there's something else for it to catch on, it'll keep going. So, where do you think I got these 2 pages? Internet. Where's a good place to look at different types of screws and stuff? McMaster. So, like, if you want to buy screws and stuff, go to Fastener or something like that. If you just want to see what's out there, I like McMaster. Because they have everything. There's not been too many odd times when I've wanted to look at something that they didn't have. I mean, they've got everything from nuts and bolts to raw materials to welding supplies to vent fans and cleaning supplies and everything. So if I go over here to screws and bolts, now what kind do I want? Do I want some screws?
520 and
I want a socket head or a cap screw or a machine screw or a set screw or a self-tapping screw or a drywall screw, lag bolts, captive screws, threaded rod, whatever. So if I wanted, let's say, a machine screw, now what kind of head do I want on it? So I can I can do these any order I want. I can pick the head, the type of material and the type of finish, the drive style, if it's intrametric, or the size, the length, if it's got a locking piece on it. So if I know I want a half 13, now I only have the option of a round or a flat head. So let's say I want to do a round head. And I only have the option of a slotted. So now do I want it steel or stainless? So I want to do regular steel. Now what length do I want? There I go. So now it gives me everything I need for that, including a drawing. So you could actually go in and download this. If you're doing 3D, you can do 3D. If you're doing 2D, save it as a PDF, save it into your project file, then you have that cut sheet. And it tells you like the hardness and the tensile strength and everything for it. And so now you can use this part number. So if you're doing a drawing for someone else, you don't care where they're going to buy it. They could buy it from Fastener or whatever. But if you give them this part number, they can come back here, look it up, and see all the specs that you want. So now all you have to do on your drawing is say, I want a half 13 round head slotted. And by, so maybe on your drawing you do it. What was my link on that? By 2 round head slotted. So you make that note on your drawing. Then you put the part number. So if they want to see the material and whatever else, they just look up the part number and they can see all the rest of it. But on your drawing, all I have to put is that little bit. Okay. What do you think? That means. No. You just told me 3 different styles. What was the H here? Head. So the H there is head still. So what do you think that is? Yeah, panhead Phillips. So panhead Phillips. So whatever the head is, then head, then the drive stock. So some other screw types. We have a shoulder screw like that. And so what's different about a shoulder screw? What's different from a shoulder screw and this? Yeah, it's got little notches here. What do you think those are? No? Talked about this in 6 the other day. Oh no. Oh no, it wasn't 6. Never mind. It was in 4C. So if we had another part coming on this, it's like that, right? If this part came here, what would be right there? A little fillet, right? So by doing this undercut, now this part can come all the way to the end. And it doesn't have to be chamfered or anything to get around that fillet. So that's one difference. The other difference you can't really tell from the drawing is that this part of it is usually ground really well, so it's really smooth, really nice finish. So it's gonna work well with another piece rubbing against it. We have the self-tappers. We got lots of different types of self-tapping screws that'll actually cut their own threads as they're going. So yeah, they have one specific for metal, one specific for plastics. And then we have wood screws, which are their own kind of thing. Wood screws, we don't have a threads per inch on them. We just call them by a diameter. What do you see here that's different from any of the machine screws or bolts we've seen? Point on the end. If you look at the body of it, they come straight, and then it starts curving down to that point. And so, because what it does is it's actually going to push the wood out of the way to hold itself in. And so what do we do before we use a wood screw? What's that called? What's it called when you drill the hole first? Pilot. The pilot drill. Do you have to pilot drill all wood screws? No. When do you need to pilot drill it? What makes you decide if you need to do a pilot drill or not?
Don't want to crack it.
If you don't want to crack it, but also what determines that? Some type of wood has the biggest part of it. So part of it is if you're going to be close to an edge, you definitely want to pilot it, or if you got a couple things. But if you, depending on the wood, if it's a real soft wood, you probably don't have to pilot it, even if you're right next to the edge. But if you're on a real hard wood, you better do it. I did a little gate thing for Mom out of red oak,
Oh God.
and it had little tiny screws. They were like, what were they? They were like number 6s.
You can break it.
They were really small, and I broke a couple and I had to go buy new, real small, so I could fit the latches and the hinges and stuff I had. My pilot hole ended up being like out here, just to catch that last little bit because of the size of the screw. It really depends on the material that you're working with, how big you need to make that. But most of the time, if you're doing like maple or something, it's going to be down in here somewhere. And again, go to Google, type in pilot drill chart and the type of wood, and you'll find tons of stuff. All right, let's go and take a break for a little bit. We'll come back in 15 minutes, so at 6:30, we'll come back.